Okay, so far we've only really considered reactions where the reactants just go ahead, turn into products, and then that's it, nothing else happens. Well, let's look at the following example. The reaction, two A's collide together, and then they just stick together. All right? I think we've seen this before, but my following question is, how do we know that these two A's stick together and then never fall apart ever again? How do we know that this A2 never falls apart into something else? It's a yes or no question. Do we know that? No, we don't. How do we know that we produce a bunch of A2s and then the A2s don't start colliding with each other, for example, and then flying apart into 4A's? Or I don't know, it just, the bond that it forms is like unstable. So it sticks together for a couple of seconds and then falls apart, right? That is an entirely possible scenario. Do you guys agree? Yes, no?
Yes.
No, okay, cool. And since this is an entirely possible scenario, now we have this thing where we're making two A's into A2s, but at the same time, we're making A2s into two A's. Back into two A's, right? And that's great. And in this case, we have a reaction that's doing what? It's going forward, and then it's going backward at the same time. Right? And we're going to now introduce this idea of having the reaction in the forward direction and in the backward direction, where if you write a chemical equation like this, the forward direction means going from left to right, and the backward direction means going from right to left. Okay? And you can technically write this equation in the opposite way, and now your forward and backward directions are different. But so essentially, forward and backward direction depends on how you write down this equation. Now, also, these arrows, don't quite copy them because that's not the correct notation. We'll introduce it a little bit later in a second. Now that you can guess, the rate at which we use up A's is going to be slightly different than what we talked about before in our rate laws, right? Because now not only are you using up A's to make A2s, but the A's are now being replenished by the fact that you do have like A2s turning back into A's. However, for the sake of consistency with last time, when we talk about the rate of reaction of like the forward reaction, we're going to talk about you're using up A's, and then once you produce an A2, it's like taken out of the thing, and you're just looking at what the A's do just on the run. All right? So the rate loss that we talked about is still going to stay the same as like some K A squared. That's what we're going to talk about. For consistency of notation, think of rate laws as still things where the forward and backward, the back feedback doesn't contribute to the rate. We just think of, okay, when we talk about the rate law, we just think of what if A was just on its own and then it produced A2s, but those A2s didn't do anything. Okay, now, what does this really mean? And how does this look like when this happens? I like thinking of it as what's going to happen if you also have this like backwards feedback when it converts backward into the initial A's. I like thinking of it in the following sense. Actually, going to ditch this reaction. I'm going to now use, I don't know, the following reaction. A turns into B, and then B turns back into A. Okay. This following reaction, because this is just easier to reason with. All right, and let's think of the rates of what's happening here. The rate of the forward reaction, Rf, I will now almost always refer to something with going forward as F subscript. The rate of the forward reaction is some coefficient for the forward reaction times the concentration of A. Do you agree? And then the rate of the backward reaction is some other coefficient for the backward reaction, Kb, lowercase kb, times the concentration of B. Right? This is what we know. Now suppose we start off with no B's at all. No B's at all. And we start off with a bunch of A's. And no B's at all. All right. Let's imagine this in the following sense. Let me get some colored chalk. Actually, is that visible? That's quite visible. That's okay. Okay. Yeah. And suppose we have A's, and we have a bag of A's, and then the reaction takes these A's, converts them into B's, right? Initially, we don't have any A's at all. Do you agree? Oh, sorry, no B's at all. We're starting with 0 B's, no product. We just started off with reactant. Okay. So we have a bunch of these reactants, right? And initially, based on our rate law, we see that, okay, we're going to have like this number per second of these turn into B's. Do you agree? So say after 1 second, I don't know, 2 of these turned into B's, right? Now, after 1 second, our rate is now slower because we have lower concentration of A. Do people agree with that? So now say instead of two A's, I'm going to have only one A turn into B. Only one A in the next second, right? I'm going to add one here. However, now there's a concentration here. So now per second, we're also converting B's back into A's, right? And suppose, because this has a low concentration, only one B got turned back into A. And now I'm going to draw this here. All right. Now, let's look at this once again. We just turned one A into a B, right? And then we turned one B back into an A. So, okay, let's do this again. I'm going to erase this one, it turns into an A, into a B. But then I'm going to erase this one, it turns into a B. Did the overall number of A's and B's change? No. Do people understand how that happened, right? At the same time, was there a chemical reaction where an A turned into a B and a B turned into an A? Yes. So, there is definitely a chemical reaction going on physically, like things are physically colliding and changing from A to B and B to A. However, we can't really detect it by measuring concentration, because concentration stays the same. And we therefore see that per second, the number of balls transferred from bag A to bag B is the same as the number of balls transferred from bag B to bag A, right, per second. Take a moment to think about that. The number of balls that went from A to B every second is now equal to the number of balls going from B to A every second. Yes?
That means we would end up like
with no B?
Yeah.
What do you mean? Why? If I sorry, go ahead.
Because it's like the same rate of like the same, I guess, number of B is being made as like A is being made.
Yes. So I make one B in here, and then one B turns into one A. So I did plus one minus one plus one minus one plus one.
So wouldn't B always be like at some point?
This would always stay the same. This will always now stay the same. Because I used up one A to make a B, so minus one plus one. But then I used up one B to make an A, so minus one plus one. But then, so that's...
At the beginning where we didn't have any B's?
Yes, at the beginning we didn't have any B's. We made some B's, right? But as we made some B's, we lost some A's. So this rate of how much transfers per second got lower because this concentration increased. Yes? And then this one, at first we didn't have any B's, but then we got some B's. So this rate of reaction increased. And eventually we leveled off so that we are producing as many B's as we're using up B's to produce A's.
But wouldn't that mean we end up with like no B?
Why would that mean we end up with no B? We use up as much B as is replenished by making A's. So once again, look at this. I'm going to use up this what's happened in 1 second. I use up one A, I erase it here, and then I turn it into a B. Do you agree? So I got minus one particle here and then plus one particle here, right? In this same second, what happened is that this B got converted into this A. So this got erased, we got -1. And then this got added, and this got +1. overall net change is 0, overall net change is 0. Does that make sense? I'm producing as much as I'm using up. So I'm not actually changing anything. There's still a reaction going on, but I'm producing as much as I'm using up. Now you have to understand that this didn't happen instantly. We first had to get to the right concentration of B's and the right concentration of A's such that this actually starts happening. All right? But the idea is that eventually this will start happening if you have a reaction that goes both forward and back. Okay, does this make sense? And now, since we don't see any concentration change, but we definitely do know there is a reaction happening, it's just that it's happening in both directions at the same speed. We call this that the system has achieved a dynamic equilibrium.
Oh, that's what our thing is called.
Yes, and our thing is called not dynamic equilibrium, it's just called equilibrium. Our today's topic. The first topic, then we have a second topic, which is an application of equilibrium. So dynamic equilibrium. An equilibrium, probably something Greek, Latin, don't ask me. Yes, and this is the part where I was supposed to say roll credits. Anyways, we've just looked at an example where we have a chemical equilibrium. Because we have a forward and a backward rate of like in a chemical reaction. It's the chemical reaction that's like making things go from this bag to this bag and from this bag to this bag. However, you can have other types of equilibrium. You can have physical, I think it's called, phase and solubility. Phase is like, if you have ice, right, and then you're at 0 degrees and some of the ice is melted, but some of it is still water. I think that's kind of how it goes. Actually, no, not with ice. It's like evaporation, sorry, my bad. If you have like a jar with water, right, and you have like it's in a container, right? Suppose initially the air in the container is incredibly dry, right? Some of the water is going to evaporate to like moisten up the air, right? And then it's at some point how much water is evaporating and how much water is then going back from the air is going to be the same per second. And it's going to achieve an equilibrium. But initially, if you start with completely dry air, some of the water is going to evaporate, but the water that evaporates, at the same time, some of it is going back into the water, and what's the word called? It's no, it's like not solidifying, it's sublimation. One of those, it's going from gas back to liquid, some of it. And that's how you kind of have, this is not a chemical reaction, this is a physical change in phase. But eventually you're going to reach a point where how much water is evaporating is the same as how much water is going back into the liquid. Sorry, how much the water vapor is going back into the liquid. And that's also kind of equilibrium. And then there's a solubility equilibrium, which is if you have, and that's more precipitation, is if you like try and dissolve something in it, like some like powder in it, then some of the stuff will stay as powder, some of it will dissolve with water. But the stuff that dissolved with water can still precipitate back. And then at some point, it's going to like reach a certain, after some time, it's going to reach a point where how much is dissolving is the same as how much is undissolving, if that makes sense. And these are cool, and you need to know these as like conceptually. You can have water evaporate and then turn back into liquid, and that could be an equilibrium reaction. And once again, it's like the same idea with bags. It's like water versus gas, like liquid versus gas, and then they turn back into each other. But these you only need to know conceptually, and you can probably do some really fun physics with it. And actually, I think the math that we're going to do with chemical equilibrium is going to be more or less the same as with the math with the chemical equilibrium would be very similar with the physical phase equilibrium and solubility equilibrium. Okay, now that we've introduced the concept of an equilibrium, we can try and see if we can describe it more mathematically, more precisely. So we can actually get a quantitative prediction of what happens when things are in equilibrium. Well, what did we notice? We noticed in our kind of thought example that how much A's are turning into B's per second is the same number of how many B's are turning into A's per second. Do you agree? So in that case, what does that mean? How many A's are turning into B's per second? That's the forward rate of reaction, right? So we get that the rate of the forward reaction is equal to the rate of the backward reaction. Do you agree? Okay. Now, we know that the rate of the forward reaction, now we're gonna flip from this kind of reaction to like a general single step reaction. So we're gonna have A1 times A1 plus, actually that's confusing notation. What am I gonna do here? Hold on, I'm gonna erase this. We're going to flip back to a general reaction. So let's do C1A1 plus C2A2 plus dot 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 C and AN. Do people understand what I mean when I write this? Yes, no? As a reaction, like these are the reactants turning into, actually, instead of A, I'm going to use R. So whoever already wrote this down for like the third time, yes, use pencil or just cross things out and keep going. And then I'm going to use, what's a C, D is a terrible letter, K. No, K is a terrible letter as well. A, B, C, D, E, F, G, H, I, J, K, L,
Q.
M, N. Let's do N. N1, P1, plus N2, P2, plus dot dot dot, plus N, oh wait, that's N, that's, no, hold up. I'm getting confused with my notation. Instead of, okay, fine. Instead of N, I'm just gonna give up and use B. B2, B, okay, BZ, PZ. Okay, sure. And also, one of the things that I wanted to introduce this notation and I forgot, like usual. Instead of, when you have an equilibrium reaction, these are called equilibrium reactions when they go both forward and backward. Instead of writing like a normal arrow, you write two separate arrows, but they're like half arrows. It's one that goes like up like this, and one that goes back with the thing facing downwards like this. Instead of like your regular chemical reaction arrow, you would write that kind of arrow. Does that notation make sense? And this notation implies that the reaction is in fact reversible. Yes. Or it eventually achieves equilibrium, or like it's possible for a B turn back to an A. It's not always possible for that to really happen, but when it is, you use these arrows. Okay. Now, let's consider our general reaction. Suppose this general reaction sometime passed, and it reached equilibrium. And we said that when something reaches equilibrium, we get that the rate of the forward reaction is equal to the rate of the backward reaction. Do you agree? That's what we said. And now let's write out the rate laws for the forward reaction and the rate law for the backward reaction. We're going to assume it's like a single step reaction, or at least the rate law matches what would be if it was a single step reaction. So we get that the rate of the forward reaction is what? It's some coefficient Kf, right, times the concentration of R1 to the power of C1 times all the other ones, concentration of Rn times to the power of Cn, right? Yes, people agree this is the rate law of the forward reaction. From last time, we talked about it.
Oh.
Yes? Okay, cool. And then, and once again, these are concentrations once they have reached equilibrium. Do you agree? So these are the concentrations once the rates forward and backward are same. Because concentrations change over time, right? This is specifically rate forward at equilibrium and rate backward at equilibrium. Because once again, we said initially we started with no B's, we waited to get some B's, and then we achieved equilibrium. And these concentrations we're talking about are the concentrations at equilibrium. And okay, I guess I could put like a little E subscript everywhere, but that would be annoying. And this is equal to the rate of the backwards reaction at equilibrium, right? And that's Kb constant, right? one of the rate constants that magical constant that we may or may not know something about, times the products, product 1 to the power of b1 e dot dot dot, product z to the power of bz at equilibrium, these concentrations. Okay, so we get this equation. Now I'm going to do a very simple manipulation with this equation. I'm going to divide both sides by this product of concentrations of R, and I'm going to divide both sides by this constant K subscript B, K backwards. Okay? People understand what I'm doing. I'm going to get Kf divided by K subscript B is equal to this product of the concentrations of products, and then the product of the concentration of reactants. Do you agree? Rn Cn. Do people understand how we went from here to here? I divided both sides by this thing, and then I divided both sides by this thing. Is that even visible here on camera? Yeah, that's actually quite good. Okay. Yes, this makes sense? People agree with me? Does it also make sense how we got from here to here? How we got from here to here? Yes? No? Not? Okay, good. Now, if we observe this very, very carefully, we get that what? Kf and Kb, they're what? Constants. So they do not change. This number is always the same, like fixed. If you have the same reaction at the same temperature, initial temperature, and it's the same reaction, this is always fixed. This doesn't change ever. However, can these concentrations technically change? Yes, because suppose I didn't start off with like no I didn't start off with like no B's. I started off with more B's than I had A's, like a lot more. Then the final concentrations should be different, most likely, right? But we know we still achieve equilibrium at some point. So okay, we are going to relabel this Kf over Kb. We're going to relabel this as capital K. And this is called the equilibrium constant. Equilibrium constant.
Wait, sorry, are the small k's individually fixed, what are you saying, or like they're like together they're fixed?
No. Individually, each one of those constants is fixed, as we remember from last time, right?
Yes.
Because we said that for a rate of reaction, now we're just going to introduce a constant that is unique to each
reaction at a specific
temperature, and we're going to say that's going to be the percentage of actually successful collisions, and we're going to claim it's fixed for a specific reaction at a specific temperature.
Okay.
And we know these are fixed for a specific reaction at a specific temperature. However, if this side is fixed, we know that this side has to be fixed, right? Overall, this side has to be fixed. They can individually change technically, but that means the other things are going to also change to make sure that this ratio always stays the same. Okay, and we're going to call this this large K equal to Kf over Kb. We're going to call that the equilibrium constant of this reaction. And why is this very, very useful? This is very useful for the following reason, that we get that that regardless of the initial concentration of how many reactants we have, we can make these like literally anything we want it to do. We get that in fact the ratios of their concentrations raised to some powers is always going to be the same at the end of when they reach equilibrium. And that's very useful, because now you don't remember how we like had to integrate and do all of this stuff to find like the graph over time, right? Now you don't necessarily like And that was already difficult enough. But now we have this idea where the reaction goes both forward and backwards, right? And that's only complicates this whole process if we were to solve this differential equation. That would make it a lot more complicated. I might show it at like the very, very end as a bonus and for fun. But it gets substantially more complicated. But this lets us use just a simple ratio, and we can technically predict what the final concentrations at equilibrium will be if we know the initial concentrations. Anyways, so this is some whatever math. Let's try and see if we can get a more qualitative hang for it. Get the vibe of what this equation really means. Let me tilt this a little bit. Okay. Okay, so now this general form of the equation is quite cumbersome, so I'm going to go back to the equation where we have just A's turning into B's.
I have a question.
Yes?
You know that graph you drew?
Yes.
Were you just explaining how it's like, we don't have to do that anymore?
Yes, you don't have to do that if you, with this idea, you don't have to do it if you just want to find the final concentration.
Oh, okay.
If you want to know the concentration over time and find the actual graph, okay, then you still have to do all the integration and stuff, but sometimes you just care about how much are you going to have in the end. And actually, the fact that you have stuff going both in the forward direction and in the backward direction complicates that by a lot, because now you can't just assume the reaction will go to completion, because like we could before. Before you could just do basic stoichiometry and say, okay, how many moles of this do I need for moles of that? What's my limiting reactant? And okay, if my limiting reactant, all of it reacts, how much do I get as a product? However, in an equilibrium reaction, you get that, hey, not everything's going to react, because some of it is going to be turning back into the reactant all the time. And that's kind of the difficulty here, how to predict that. Anyways, let's actually look at the following reaction. We're going to have two A's. No, we're going to have the reaction where, let me think about this. Yes. Two A's are going to turn into A subscript 2, right? What are the forward and backward rate laws? The forward rate law, forward rate is the forward constant times A squared. Do you agree? Yes? I need nods or yeses out loud.
Yeah.
The backward is just K backward times the concentration of A2. Okay? So I'm going to once again do the exact same thing to get the equilibrium constant. We're going to equate them, get Kf of A all squared is equal to Kb of A subscript 2. Is this all like readable? It's fine? Okay. And then we're going to divide both sides by concentration of A squared and both sides by Kb. We get K forward divided by K backwards is equal to the concentration of A2, which is our product, divided by the concentration of A squared, which is our reactant. Okay, and this is overall some constant. This is a fixed number at equilibrium. Do you agree? Okay. And now consider the following graph. So we now have this fact, and now we have the following graph. The x-axis is just time progressing, and this is the concentration of A. Okay, and I'm just sketching this graph so we kind of get a general hang of it. So okay, A starts at some initial concentration, it goes down, and then it levels off and it reaches equilibrium somewhere here, right? The concentration stops changing. This is the concentration, right? Suppose here it reaches equilibrium. Okay, and then it goes along, and say now, I'm an evil person, the reaction is already at rest, it's done everything it can, it's just, converting back and forward at the same rate, it's stable, it does what I was doing, but I'm an evil person, I want to mess with things. So I'm going to increase the concentration of A. I'm going to A is a powder, and I'm going to add it to my solution, mix it really fast, and all of a sudden I'm going to increase my concentration of A. Right? Do you agree? The question is, this is like an instantaneous increase of concentration. The question is, what is the reaction now going to do? Are we going? What am I going to start making, or is the reaction going to do anything at all? Is it going to increase? Is it going to stay the same, or is it going to decrease? Decrease. Now let's think in terms of this equation why that would be the case. Well, first of all, why can it not increase? Before, my rate of the backward reaction and my rate of the forward reaction was the same, right? But now I increased the concentration of A. So my forward rate increased of me losing A's, that increased. But the backward rate, I didn't do anything to A2's. So that means the backward rate stayed the same, the forward rate increased. So it can't go up just by the rate loss, right? I have to start using up these A's faster than I replenish them. Okay, and that's why it also can't stay the same. And that's a way to reason with this using rate loss, right? However, we should use this equilibrium constant instead, because this is much easier than writing out a bunch of rate loss. This is two equations, this is one equation. In this one equation, we know that at equilibrium, these guys, this ratio should be the same, right? So, the ratio was this ratio at here. But then, all of a sudden, I increased this number. I increased the denominator of the equilibrium constant, right? But we want these concentrations to balance back out, so it's still the same number as K. If this number went up, that means to balance this out, this number has to go up and this number has to go down, right? Because that means if I increase the denominator, the number overall got smaller. Do you agree? To make the number bigger, to make this ratio bigger again, back to the same value as it was at equilibrium, I have to increase the numerator and decrease the denominator. And turns out decreasing A also increases A2 at the same time. Okay, does that make sense? So my graph is going to look something like this, and then it's going to back to equilibrium. But it's not going to quite go back to the same or initial value. Why is it not going to go back to the same initial value? Because that wouldn't make sense, because I added more A's. I can't end up with the same number of A's and the same number of A2's after I've added more A's. That just doesn't make sense. You can't add something and then end up with less. Okay. Now we're going to do something a little bit more tricky. I'll give you a second to think about it. Does this make sense? Like, why this number has to increase, why this number has to decrease? Yes? No? Okay. Now, let's look at the following case. Suppose, okay, it reached its new equilibrium position. But now, I decide to increase the temperature. Temperature goes up. Okay? Now, clearly, this part of the equilibrium constant isn't useful for temperature, because this has to deal with concentrations. Do you agree? This is like this really doesn't help us. However, which part does help us? It's this part. Right? Because we can write out equations of Kf and Kb in terms of the Arrhenius equation. And that one does have temperature in it. Right? You guys agree? So I'm going to write that out on that board. We're going to have A for the forward reaction times e to the negative activation energy divided by, for the forward reaction, divided by R times the temperature, divided by A of the backwards reaction, times e to the power of negative activation energy for the backwards reaction, divided by R of t, right? We get this number. Mm-hmm. And because we're dividing is subtracting, we're dividing powers of e, dividing e by e, so we can subtract the powers. This is going to be equal to AF divided by AB times e to the power of negative activation energy S RT plus the activation energy of the backward reaction divided by RT. Okay, this one's a bit confusing, but hopefully it's going to make sense. Okay. Do you guys agree with how I got this? And this is still the same old equilibrium constant. This is still the same equilibrium constant. Yeah? Do you guys have difficulty with like reading any of the letters? Should I say something?
It's okay.
This is supposed to be a V. I'm sorry. EA underscore V. It's like a subscript on a subscript. Alright. Actually, maybe I should have hit record here too, but actually you can't see the laptop and no one joined, so that's fine. Okay. Are people done copying that down? Yes? No? Yes, we're good? Okay, so now suppose the temperature increased, right? So initially this number at our initial temperature, this was our equilibrium constant. Do you agree? This was our equilibrium constant. This was the ratio of these two guys, right? Now the temperature increased. So both of these numbers got smaller, right? Do you agree? This one and this one got smaller. But they didn't get smaller by the same amount. Do you agree? So now, overall this number, depending on what EA of F is and what EAB is, this number can either go up or go down. Right? Our temperature changed, our equilibrium constant can either go up or go down, right? Suppose, and we need to know EA or F and EA of B to see which one it is. Okay. Suppose the equilibrium constant increased. Right? As we increase temperature, suppose the equilibrium constant increased. If the equilibrium constant increased, right, with temperature, what must happen for to these concentrations for them to match the fact that the equilibrium constant increased? This ratio also has to increase. So what do I need to make more of? A2. So I'm going to use up some A's, make more A2s. And okay, suppose the equilibrium constant increases in this case. Actually, no. Now suppose the equilibrium constant decreases, right? What do I need to make more of? A. Now I need to go in the backward reaction. And in this case, we say the equilibrium shifts, like, to the left. The equilibrium shifts left. And in this case, that means I'm going to have less of A's, right? And okay, I'm going to have, like, it's going to go down, like this. Now, the question is, how do we know if it goes up or down, without knowing the activation energy? Well, and doing like complicated inequalities with it. Not too complicated, but annoying, for sure. Well, I'm not going to exactly explain it, and like derive it fully with math. I'm going to intuitively motivate it. Suppose this forward reaction is, so I said that the A has to decrease. Suppose that the forward reaction is endothermic. Do people remember what endothermic is? That means that the change in enthalpy is positive. So the reaction takes in energy from the environment. Do you agree? So now, suppose I heated up the environment by a bit. The reaction doesn't like that. It liked its old temperature was at. It doesn't want to go from it. So it's going to react in such a way that it's going to try and decrease that temperature back, right? So if the forward reaction is endothermic, it means the backward reaction is exothermic. If I increase the temperature the reaction wants to decrease that temperature back of the environment. And how can it decrease the temperature of the environment back? It can use up the new temperature energy with the new temperature to react forward into the endothermic reaction, use some of it up, and decrease the temperature that way. Does that make sense? No.
So if we're trying to decrease the,
If this is an endothermic reaction in the forward direction, right? And the reaction reached equilibrium, it was having a great time. Then I decided, hey, I want to increase the temperature of the environment the reaction is in. Reaction doesn't like that. It wants to undo that change. It wants the temperature to go back down. The reaction, it's a reaction. The only thing it can do is react either forward or backward. It can't do anything else. Like it can't turn down the thermostat. Unable to do that. Doesn't have hands.
like, so for this case, we're looking at the reaction, the rate of reaction decreasing.
The rate of reaction changes. We don't know if it decreases or increases.
Okay.
Forget about this then. This was just like an intuition that the
So
rate.
we're not looking at the part of the graph that goes after.
Well, this does describe what this happens. When this happens. So let me try again. The reaction reached equilibrium here, right? It's having a great time. And it's an endothermic reaction in the forward direction. I increase temperature. Reaction doesn't like that. It wants to undo the fact that temperature increased. It wants to make temperature go down. So it wants to do something that uses up energy and takes the energy out of the environment to lower the temperature. But the reaction the only thing it can do is react either forward or backward, right? So which way should the reaction react so it uses up energy from the environment? In the endothermic forward direction or the exothermic backward direction? In the endothermic forward direction. Because endothermic means that the reaction gains energy, so it takes energy out of the environment. So after I've increased temperature, the reaction shifts to the right, so A's get used up to make A2s to decrease temperature, and therefore the concentration of A goes down.
Oh.
Yes?
Is the forward reaction always endothermic?
No, it can literally be anything. I'm just giving this as an example. Suppose it was.
So,
I could write A2 turns into 2A, and now the forward reaction's exothermic. I can just flip them.
the K constant should get, the ratio should get smaller?
The ratio,
Or no, it should get bigger?
the ratio should stay the same,
Okay.
but these quantities, no, sorry, you're right. And because this is an endothermic reaction, once we've increased the temperature, the equilibrium constant itself changes, right? And that means that the ratio should get smaller, you're right.
Okay.
Well, actually, no. The ratio should get bigger because you want more product. You want to be making more of A2 to use up the energy. So the
So you should
top
be-
gets bigger, this gets smaller.
So yeah, so it should be the a ratio of the concentration
Of A turns into A2.
Okay.
Yes. However, now we don't need to know any of these activation energies. We kind of had this intuitive method that the reaction wants to undo whatever it was doing. Oh, I wasn't showing that. The reaction wants to undo whatever it was doing and react in the right direction to use up or exert more energy. So, for example, if I lowered the temperature, right, then the reaction would want to make more A's, because this way it releases energy back into the environment. It wants the temperature to go back up. And this gets us to the fall. Okay, does this kind of make sense intuitively? Okay. So now we've seen that the reaction, an equilibrium reaction, once it has reached equilibrium, if we disturb that, if we change, for example, the concentration, right, then we saw that it kind of tries to go back. And we understood that from this equation, right? And then with temperature, we realized that it could do either thing, but we kind of reasoned that it probably should also go down if it's an endothermic curve reaction. So we get that after we change something around the reaction, it said, hey, I don't like that. and I'm going to do whatever I can, which is react either forward or backward, to undo that change. And this is a pretty good way of qualitatively thinking about it, so you don't always have to like write out these ratios and formulas and so on and so forth. We get the idea of the Chatelier principle. Chatelier's principle. And this principle is purely qualitative, but it's really helpful at drawing like the graph, the kind of graph that I drew where something turns into equilibrium, then say we increase concentration, what happens? Like we increase concentration of A or B, what happens then? And Chatelier's principle, I think there's like some formal phrasings of it. I phrase it in the following way, which I find to be the most simple. If a change is made to the equilibrium system, the reaction will react in the direction to undo that change. The reaction always wants to undo whatever just happened. It really doesn't like change. So if a change is made, to the equilibrium system, the reaction, the equilibrium reaction, okay, yeah, that's visible, reaction will react in the direction, this is horrible handwriting, in the direction that undoes this change. Undoes this change. That change. Okay. So whatever happened, you just want to undo it. But the only way you can undo something is react either forward or backward, because you're a reaction. All you can do is react. Okay, does that make sense as an idea of how equilibrium acts if you try and change it? Yes? No? Okay. The system always tends to to equilibrium. And to achieve equilibrium, it just tries to undo whatever stress just happened to go back to equilibrium. Yes? You look confused. Are you okay? Are you okay?
I'm right.
Okay.
I am.
That's fine. Okay, I'm going to give you guys a second to write a little bit more. Yes. So actually the graph that I drew there, where like the reaction reaches equilibrium and then something happens, actually this was like concentration went up of A, right? And temperature went up, and then you gotta plot what happens to the concentration of A after these things happen. This is like a really typical IB problem that you can get. But once you understand that you're just trying to undo whatever just happened, you just have to figure out which way the reaction reacts to undo what happened, this question becomes incredibly easy. Does it intuitively make sense? Yes, no?
Yes.
I am now going to do one final example with this. And we're going to now introduce states. Suppose this is a gas and this is a solid. I don't know how this reaction would work. It just goes from gas to solid, but it does. Okay? And now suppose I still have this same kind of graph. This is the concentration of it. The reaction concentration starts with some A, it goes down, okay? And then we achieve equilibrium somewhere here. We achieve equilibrium. I've been going along, and all of a sudden, I'm going to increase I'm going to decrease pressure. So pressure goes down. By Chatelier's principle, what does the reaction want to do? I'm not asking what direction it wants to go, and I'm asking you what does it want to do to the pressure? If pressure went down, the reaction wants to bring the pressure back up. So now we just have to look at this reaction very carefully and decide which direction should we react to increase pressure. Okay. Now, this side are gas particles. Do gas particles, the number of gas particles contribute to the pressure?
Yeah.
Yes, because we remember we have like PV, nRT, and whatnot, right? And if we increase N, then P has to go up. And we haven't changed volume. I'm assuming we haven't changed volume. Just decrease pressure without changing volume. Okay, do solid particles really change pressure? Do solid particles affect pressure? No. And okay, we decrease pressure, so we want pressure to go back up, right? So, which thing is more favorable to make? The gas particles that do affect pressure, or the solid particles that don't affect pressure?
What?
Yes, we want to make the gas particles, because they are going to increase our pressure back up, right? So that means the equilibrium shifts in what direction?
Left?
Left, okay. And you should get used to writing the word equilibrium shifts in left direction, because that's just the notation we use. The words, the terminology used, not the notation. Okay? And in this case, what is this graph going to look like? It is going to increase and then level off again. Does that make sense? Because we wanted making more A's increases our pressure back up. And by Chatelier's principle, if we decrease pressure, we want to increase it back up. So the concentration of A will increase and then level off again at equilibrium. Does that make sense? Yes? So this principle really works with a lot of things. Like a lot of things. Okay. And you should be able to draw these graphs, but I mean, once you get some practice drawing these, and this is a question of practice. Does the principle itself make sense as to why we go one direction or the other? Okay. Yes.
We say the equilibrium shifts.
Pardon?
We say the equilibrium.
Yes, we say that once you've achieved equilibrium, we add a stress on it. The equilibrium shifts right or left, so to either make more of product or more of reactant, to undo that change. And we say the equilibrium shifts when after you've achieved the equilibrium, the reaction starts reacting again one way or another in response to a stress that you've added onto the system. Okay, what was I supposed to say? Okay, yes, very cool. No, it's kind of going according to plan, quite well. Okay, I think I'm going to use that board now again.
No chocolate chip cookies.
Yes.
So far.
Okay, so this is great. But these kinds of graphs aren't terribly useful. Okay, I know if it's going to increase or decrease, but I want to know exactly how much it's going to increase or decrease. And in general, we haven't even figured out yet how to figure out what the equilibrium concentration is going to be at this point, just after we started. We can't even do that. Well, we're going to once again consider this reaction. It's very simple reaction, because it's just simple. Actually, wait, is that the reaction I prepped for us? Wait, no, I prepped a different reaction. Actually, yeah, we're going to use a slightly different reaction, but it's kind of the same thing as that one. But this one's better. So suppose we have A plus B is an equilibrium turning into AB. Do you agree? Yes? I need nods or something. This is very simple, makes sense. Suppose our initial concentration of A0 is equal to, say, 1 mole per liter. I'm just making the numbers like simpler. And then our initial concentration of B, B0, is equal to 0 moles per liter. Right? We're going to pose the following question in front of ourselves. What are the equilibrium concentrations of A, and what are the equilibrium concentrations of B? And what is the equilibrium concentration of AB? Does that make sense as a question to ask? Does that make sense why finding this exact number would be hyper useful? Because, okay, then you can actually predict how much product you're going to get. That's already great. And I'm also going to say that our equilibrium constant K is 10 to the negative 4. We're given these pieces of information. Yes. And you can always measure the equilibrium constant by just letting the reaction go with any initial concentration, regardless of what it is. Just let it be for like some arbitrary period of time. Then measure concentration of A, then measure concentration of B, measure concentration of AB, and then you can get the ratio. You can just directly measure it, right? For a specific concentration. But we know that because it's the ratio of two constants, regardless of what the initial concentration was, the ratio will always be the same of the final like equilibrium concentrations. So we can do this experiment and compute K for some initial concentration, and then that equilibrium constant is going to be the same for all initial concentrations that we can start with. Does that make sense what I'm saying? It's not terribly confusing. Yes, okay. So now let's think of what happens. We let this reaction go, and then it goes to equilibrium, right? So then we have some equilibrium concentration of A. We have an equilibrium concentration of B, right? And then we have an equilibrium concentration of AB. Oh wait, sorry, I messed up. Sorry, concentration of B is 1, concentration of AB is 0. My bad. I messed up. I'm sorry. Is 0, okay, 0 moles per liter. So as in, we start with 1 of A, 1 of B, and no product at all. That's what I meant to say. I had it. A and B and AB are very similar. And then the equilibrium constant is still 10 to the negative 4. And these concentrations somehow change, and in the end, we get their equilibrium concentrations, right? Now what can we notice? Overall, how much of AB we made, right, should be the same as how much A we used up and how much B we used up. Do you agree? So in that case, what should the equilibrium concentration of A be? It should be the initial concentration of A minus the equilibrium concentration of AB. Do you agree? So this is the initial concentration of A minus the equilibrium concentration of AB. What about B? B should be the exact same. Do you agree?
Yes.
It should be the initial concentration of B minus the equilibrium concentration of AB. And now we know these numbers because we can like measure how much A and B we put into the reaction. That's easy. And so in this equation, we know this number, we know this number, but now we have only one variable that we do not know, right? So we need another equation to be able to get the answer. Well, we have this equilibrium constant. But what's the equation for the equilibrium constant? The equation for the, actually, I am gonna, okay, actually that's it.
Oh, it's
The equation for the equilibrium constant is what?
AE over B.
Pardon? Say that louder? I just didn't hear.
AE over B.
Concentration of AB over the concentration of A times the concentration of B.
Okay, yes,
Right?
that's exactly what I said.
That's exactly what you said. It's easy to remember, it's always products over reactants.
Okay.
Very easy to remember. Yes?
Mm-hmm.
And remember that if we had some like 2's in here and whatnot, first of all, there would like be a 2 in scaling factor of 2 somewhere here, because we'd be using 2 A's for each. Maybe it's actually it'd be like 1/2. Yes, it would be 2. But like if there was a 2 here and this was A2, right? Then for every one of A2B I make, I used up 2 A's. So I'd multiply this by 2. Does that make sense to people? If that was here, that would be the case, right? I mean, yeah, and okay. Also, if there was a 2 here, this would also be squared. People realize that, why that is the case. Because we got this equation from the rate laws.
Oh, okay.
And the rate laws are this tells us the total possible number of collisions, and to do that, we multiply that to get the pairs, right? Okay, makes sense. And but we don't have that here, because otherwise this equation would be complicated to solve. So we just have like simple ones, and then it's all easy. We just have AB. Okay, we have this, and these are all equilibrium concentrations. Do you agree? So I can rewrite, and I know that this K is in fact a number, 10 to the negative 4, right?
Mm-hmm.
So I can rewrite this as 10 to the negative 4 is equal to what? Is equal to the final concentration of AB. Actually, let's relabel the concentration of AB, the equilibrium concentration of B, as X. Because writing this is just cumbersome. All right? The concentration of AB at equilibrium is just X. Do you agree? X. The concentration of AE is A naught minus X. Right? The initial concentration of A minus X. Right? And the equilibrium concentration of B is is the initial concentration of B minus X. Do you agree? Okay. Do people understand how we got this equation all of a sudden? Yes. Now, how many unknowns do we have in this equation? Things that we do not know. Do we know A naught, the initial concentration of B? Yes, we measured it. It's 1. I'll replace this with a 1 in a second. Do we know the initial concentration of B? Yes, we measured that. Do we know what 10 to the negative 4 is, which is our equilibrium constant? Yes, because we said we did an experiment earlier. So now, can we solve for X? We have one equation, one unknown. We can easily solve for X. Now, we're going to solve for X in just a second. However, people understand how we got these equations, right? And this is, in fact, as you might remember from grade 9, this is it's like a system of, all of this is, these 4 is a system of equations. We remember what systems of equations are from grade 9. Now, then remember that we're in a chemistry class. And equations, and anything that has the word equation in it and doesn't have chemical in front of it, too difficult. So writing this out as a system of equation, because we're chemists, is all of a sudden now impossible, because we just don't understand what that is and what that means. So instead of writing this out as a system of equations, we're going to write this out as a chart, because that's apparently easier. We're going to call this chart an ice table.
Ew.
I know, ew.
Ooh.
We gotta make things simpler for the
chemists.
Yeah. Ice, this is I stands for initial, C stands for change, and E stands for equilibrium. Has nothing to do with actual ice. And I find that very disappointing.
They were so clever with this.
Yeah, I know. And we're gonna make this chart, and I've already messed up because this can't go up higher. Okay, well.
Wait, does it say equilibrium?
Initial, change, equilibrium.
Okay.
Starts with an E, not an I.
Equilibrium.
Equilibrium. Okay. Dry scan. Okay. And what are these columns going to be for? These columns are going to be for the concentration of, sorry, I forgot. Our reaction was A plus B turns into AB, right?
Yep.
Okay. So this is going to be for the concentration of A. I messed up, I wrote it too high, but that's concentration of A. This column is going to be for the concentration of B. And this column is going to be for the concentration of A, B, E. Do you agree? right? Yes? And now we can fill out these numbers. Our initial concentration was 1 mole for A, 1 mole per liter for B, and 0 moles per liter for AB. Oh, oops, there's no E here at the end. Do you guys agree?
Yes.
All right. Now, we say that the change is like how much the concentration of each one of these changed by. This one decreased by, say, negative x. We're just introducing a variable, which is the change of how much the concentration changed. B also changed by negative x. AB, it increased because that's the product, so we got plus x. Do you agree?
Yes.
Then at equilibrium, our concentration of A, the equilibrium concentration of A, is 1 minus x. Equilibrium concentration of B is 1 minus x. And the equilibrium concentration of AB is x. Yes. And so we get that this specific cell is the equilibrium concentration of A. This is the equilibrium concentration of B. This is the equilibrium concentration of AB. Okay. And now, this is the same as us writing out this system of equations, that chart. But that chart is, I guess, I mean, it's simpler and it's a little bit quicker. It's more visual, so it is a kind of improvement.
Chemists and their charts.
Yeah, I mean, no, like this is an improvement to do it like faster and have to think less about it. Okay, and then we just write down that, hey, our equilibrium constant was what? It's AB at equilibrium divided by A at equilibrium times B at equilibrium. And then, using this chart, we get that this is just x divided by 1 minus x squared. You guys agree? Yes? And then we know that this is equal to 10 to the negative 14, because we said that's what the equilibrium constant is. Now we've got to solve this.
What was it, 4?
Oh, it's negative 4, yeah, you're right. Negative 14, I'm jumping ahead a little bit to other cool numbers that have 14 in them. Okay, we have space here, okay. And as you can see, same equation here, I just, instead of A naught, I plugged in 1. Okay. Remember how I asked you guys to remember how to solve quadratics?
Yeah.
Well, this is a quadratic equation, and we're going to solve it on this board. Okay. Did I actually write down how I solved it, or did I just write down my answers for it? Yes, I just wrote down my answers because I'm so great.
You're
Okay.
Too smart for us.
No, I wrote it out on a separate piece of paper and decided not to bring it. So we're gonna hope that I don't mess this up. So 10 to, you know what, I'm gonna leave 10 to the negative 14 as k for now. K is equal to x divided by x minus, 1 minus x squared. 1 minus x squared. 1 minus x squared is actually the same thing as x minus 1 squared. Do you agree? Does this make sense why I can just flip the negative inside? Because I multiplied by negative 1 times negative 1, right? This is two separate brackets, 1 minus x times 1 minus x. I multiplied negative 1 times negative 1 gives us 1, so I'm just multiplying by 1, right? But I factored 1 negative 1 inside one bracket and 1 negative 1 inside the other bracket. So the signs flipped, right? Because also x minus 1 is negative of 1 minus x. So it's like negative 1 minus x times negative 1 minus x still gives you 1 minus x squared. Okay, cool. Because negative 1 gives us 1. Okay, good. Easy. Now we can multiply both sides by x minus 1 squared. So we get k times x minus 1 all squared gives us x. Do you agree? Yes?
Mm-hmm.
Now, moment of truth. What is x minus 1 squared? How do we expand just x minus 1 squared? X squared, okay. Minus 2x plus 1, okay, good. Already doing better than some university students. That's great.
Slay.
Exactly. Now, I'm going to make this easier to write down, I'm going to assume k is not 0. I'm going to divide both sides by k. Because that way it's just, yeah, I have to write less k's. X squared minus 2x plus 1 is equal to 1 over k times x. Do you agree? Yes? People agree. Now I can subtract 1 over k times x from both sides, move it here, and get x squared minus 2 plus 1 over k times x plus 1 is equal to 0. Do people agree with this? Do people understand how we went from here to here? Yes? Yes? I subtracted, so does it make sense how we got from here to here? Yes. I subtracted this from both sides, and then you have minus 2x minus 1 over kx. So I factored out the x from minus 2 and minus 1 over k. So minus 2 plus 1 over k, because the negative gets distributed inside times x. Yes? We're good? We're good. Okay. Now we can just plug in the quadratic formula. What do we get? We get that x is equal to x is so what? Normally it's negative b plus minus square root of b squared minus 4ac divided by 2a. Do you agree? Yes? In this case, our a is what? Our a is 1. Our b is negative 2 plus 1 over k, right? And our c is 1. So we get it that in this case, we have negative of negative 2 plus 1 over k. Do you agree? Plus minus square root of what's it called? Of x squared minus 2 of 2 plus 1 over k squared minus 4 a times c. A and c are just 1, and then divided by 2. Do you agree? Then I'm going to plug in my number for k. I'm going to get that this equals to this equals to 2 plus 10 to the 4, just 10 to the regular 4, because k used to be 10 to the negative 4. When we do 1 over 10 to the negative 4, you get 10 to the 4. Yes, people, that makes sense to people? 2 plus 10 to the 4 plus minus square root of 2 plus 10 to the 4 squared minus 4 divided by 2. Okay, do you agree with this statement? Okay, well, we have the following problem here. We have two possible roots. We have a plus root and a minus root. However, it doesn't sound likely that our equilibrium concentration will be two different concentrations. Like it should always keep doing the one thing. Well, if you compute the plus and minus roots, and you use your calculator, or in my case a computer, if you take plus, x plus is equal to approximately 10,002, right? And our minus root, x minus, is equal to approximately 1 times, it's equal to 0.00009998, which honestly looks very close to approximately, so that, actually let's write that in scientific notation. That's that's 9 times 10 to the negative 5, but honestly you would round this up and just write 1 times 10 to the negative 4. Okay? People agree with that? This 99998, that's like 1 times 10 to the negative 4, really. So this is like, ignore that. Just 1 times 10 to the negative 4. Now we have these two roots. And which one of them is the right one? How do we know? Well, what was x? What did x represent?
AB equilibrium. Wait a second.
Think about the ice table. Think about the ice table. What did x represent?
The change.
The change in concentration. So we started off with concentration of 1. And then we had 1 concentration. And then our concentration went down by 10,002. Does that sound possible?
No.
That we end up with a concentration of negative 1,001? Exactly. So probably not this answer. This answer, 1 minus like 1/10,000th of 1, yeah, that sounds legit. So then we can say, hey, our final concentration of A is going to be 1 minus that number, B 1 minus that number, and X is going to be that number. Okay, straightforward. We've now figured out how to compute the concentration of something after equilibrium using a nice chart, or equations if you still feel like it. But the chart is honestly quite useful, regardless of how much I make fun of it for no good reason. Well, okay, that's one thing. But you know, once again, we're still chemists. We're doing chemistry here. And solving quadratic equations is just so difficult. It's just so difficult. So we introduced the following approximation. And I mean, the approximation is, even though you technically don't need it if you get a quadratic, because you can always solve a quadratic. This approximation is really only useful when you have like when you have like another thing, and it's not just AB, it's like A squared. Then you get a cubic here. And then a cubic is like actually difficult to solve. Then you need the approximation. Yet IB for some reason still always gives you quadratic questions where you use the approximation, and I find that just why you don't need to. But okay, it's fair. You should understand how this approximation works. You use this approximation in the following case. If you take your initial concentration of a reactant, initial concentration of A, divided by your equilibrium constant. If this is greater than the number 500, some people say the number 100, but I think in our school we say 500, because why not? So some like on YouTube, all YouTube videos refer to it as the rule of 100. In our school, for some reason, they always refer to it as the rule of 500.
We're special.
So
We're just special,
then
yeah.
we're like totally.
No, it doesn't matter. Rule of 500, they still get what you're talking about. It's good enough.
Just like,
Because they always make it like
the rest of the world.
quite large. Yeah, just better. Okay, then we can use the following approximation. We can approximate the fact that A naught minus X, minus the change in concentration, is approximately equal to the same initial concentration.
that is. So because it's like minus.
Yes, this is just kind of says that how much the equilibrium shifts by is going to be very negligibly small compared to where you started off as. Now, to me, it's actually not entirely initially clear where this comes from. So let's quickly write it out.
Wait, what is this called? The rule of 500.
Rule of 500 or 100 or something.
Rule of a really large number.
Yes, I mean 500 is really not that large, because I can write it down, so it's not that large. I can probably count to 500 if you give me enough days. So I'm going to keep messing up, but it's going to take me a while. Yeah. Plus I need to get 500 apples, so I can, and large enough baskets for 500 apples, so I can be moving baskets. You know how expensive apples are these days?
Are they?
Oh,
It's not the season, right?
really?
So it's going to.
Are you cheaper
Yes,
now?
all fruits don't grow all time of the year,
Yeah,
guys.
but is it cheaper now because they're not as good?
I don't think so.
I don't think.
Okay. So let's actually figure out why this kind of implies that. Because like it's great that I told you that it does this, but why? Well, let's remember what our equilibrium constant is. Our equilibrium constant, A naught, is the concentration of our reactant at equilibrium divided by the concentration of A. Wait, hold on. Let me think about this. I thought about it differently last night at 1 a.m. That sucks. It's gonna get a little bit more confusing than it has to be. What did I even do there actually? Yes, that's what I did.
Wait, this is just the derivation, right?
Yes. Not a derivation, just kind of intuitive explanation. Not really. If you don't have to write this down if you don't. So we can divide both sides by 500 and multiply both sides by that fraction. So we get that 1/500th of the initial concentration. Oh wait, sorry, these are supposed to be at equilibrium, right? 1/500th of the initial concentration should be greater than whatever the whoa, sorry, hold on. What am I saying? Let me double check what I'm saying. Is what I'm saying in any way reason? Yes. AB divided by the equilibrium concentration. So we get that this inequality is the same as this inequality. I just rewrote them. Okay. So we get that 1/500th of the initial concentration of A, half a percent, that is, right? Yeah, 0.5%, I think. Wait. No, well, like 0.2%. Yes, 0.2%.
We're chemists.
Exactly. 0.2% of the initial concentration is much greater than what I'm going to produce divided by what I'm going to be left over with from AE. So we just know that the initial concentration is going to be way bigger than what my change in concentration is going to be. Because if I had a really big change in concentration, this denominator would be really small, this would be really large, and like this would be overall a large number, because I'm dividing by larger by smaller. Versus this is like a 500th. So okay, this implies that this is going to be way greater than what I'm going to actually produce. Right? This is going to be still a smaller number, and this is going to still be a bigger number for this to kind of hold on. Intuitively, yes, kind of makes sense. Okay. The way I initially wanted to explain it, I wanted to explain it in a more general way, and the more general way might be a little bit clearer, because there you don't have A's. The general way is like the concentration of your reactants divided by 500. The concentration of your reactants. Yes, sir. The concentration of your reactants divided by the equilibrium constant has to be greater than 500, right? Concentration of your reactants divided by the equilibrium concentration of your products divided by the equilibrium concentration of your reactants greater than 500. Well, actually, no, I think that's like the exact same thing as what I wrote. Yeah. The initial concentration of your reactants divided by 500 is greater than the products over reactants, and so 1/500th of the initial concentration of reactants is greater than the percentage of products you have to reactants. So it's still the same idea that your change is very small compared to the initial. Okay, but
Everything you just said is like.
this makes sense. If this, then you can do that.
Okay.
Okay,
It's the half.
that's it. Don't worry about this. Because I honestly still don't I kind of get this rule as of a couple, I don't know, last year, but not really still. Okay, now let's see if what happens to our equation here if we finally use the approximation. Okay, let's swoosh you down. And now, yes.
Is it possible to write on the blackboard at the very
At the very top, yes. I just want to see these side by side,
No, I know.
Okay, so if 1 minus x is approximately just 1, this equation all of a sudden becomes x divided by 1. Do you guys agree with that?
What?
If 1 minus x is approximately equal to 1,
Oh.
1 minus x, we replace that with 1. So you get k is equal to x divided by 1.
This is crazy.
What?
Then x is equal to k.
Oh.
And k was 10 to the negative 4, right? We look at the answer that we got. It was approximately 10 to the negative 4 units. Yes, people agree?
Oh.
The answer we got with the exact way to solve it is more or less the same as that, with the approximation. It's like literally the same number.
That's crazy.
That is crazy.
Yes.
Crazy.
So once again, this approximation does make sense to a certain sense. And in a certain sense, once again, if you had like a cubic equation, you had like a plus b plus c turns into abc, then you would really need this. Because then like you have a cubic equation, and cubic equations, we can solve them, but only very few people know how to solve them. Yeah. Now, the issue is we assume that this gives us that A0 is actually very small compared to the initial concentration. That the change in concentration is very small compared to the initial concentration. In fact, now we should probably check that that is the case. And I think the default standard, you have to check that it's like less than 5% of the initial concentration. Well, the initial concentration was 1 times 5%, 0.05, that's 0.05. Okay, and this is still way greater than 10 to the negative 4. So we know, okay, therefore, we use the approximation correctly.
Wait, sorry, what's the thing? What's the 0.05?
It's a standard thing. Once you've used an approximation, you've used this assumption that A0 minus x is approximately A0. That x is negligibly small compared to A0.
Oh, we have to check
So we
it.
should check that that is actually true. And to check that, people chose like, hey, let's check that it's less than 5% of A0, and then it's fine. A0 is 1. 5%, getting 5% of 1 is times 0.05.
Okay.
We get that that's 0.05, and that's still way greater than 10 to the negative 4. We used the approximation correctly, and it worked. Now, I'm going to be honest with you guys. Equations like this aren't going to be always that easy. You aren't just going to get a 1 at the bottom all the time. Sometimes it might be a 2.
Oh my god.
Sometimes it might be a 2.5. Sometimes you are going to have 2 products at the top. You're going to have x squared at the top. But at the bottom, you're always going to be end up with some number. So you're just going to have like x equals to k times a number, or x squared is equal to k times a number. And that's more like way easier than actually solving the quadratic.
I really like this hack.
Yes. Cool. The issue is, you always have to, at least the issue was for me, you always have to double check if the hack is applicable. You always have to check if the initial concentration divided by k is greater than 500. So even if it is applicable, then you must solve the question using the hack. And that's annoying because I once on a test forgot to check for it and just solved it exactly and got marks taken off. Even if you have the correct answer, you didn't solve it using the rule of 500. So okay, you failed the test. I did not fail that, but you failed the question. Get like a mark or something. Doesn't matter. But then if the rule of 500 doesn't apply, well then you gotta solve it. And okay, cool. Get good.
Get good.
Skill issue. All right, now I have like a miscellaneous bit to show you guys.
Oh, okay.
It's kind of miscellaneous because it doesn't quite tie in with all the other stuff we're doing. Can I erase Chatelier's principle?
Yeah. He's French, right?
Yeah.
I love French people. This is on recording.
Yeah, this is on recording. Don't worry. You guys are probably not going to look at these again, so that's fine.
Who is going to?
Hmm?
Hopefully not Valkyrie.
Oh, actually, no, that'd be great. I want to see what she thinks. Okay. And actually, like last time,
Yesterday.
okay.
Wednesday.
Right. Remember how we introduced on like Monday, day one with energetics?
Yeah.
We introduced this idea of Gibbs free energy.
No, we didn't.
Gibbs free energy was like the total energy minus the energy you used to expand.
Oh yes.
Total energy minus energy used to expand. Well, it turns out that if you have a reaction, A converts to B, the Gibbs free energy is equal to negative, oh wait, that's not it.
My notes are so much neater on the first day.
Negative R, yes, because I talked better on the first day. I was more prepared. Negative R T ln of the equilibrium constant for this reaction. Turns out this formula holds true. If you know the Gibbs free energy for this reaction per mole of reactant, then this equation is true. And this is kind of cool because now, if you know your the equilibrium constant at a certain temperature, right? Then you can find the Gibbs free energy, and then using the Gibbs free energy, you can find the equilibrium constant at any temperature, and that's useful, right? Now you could also waste time writing the equilibrium constant out as like e to the power of negative EA divided by RT, and finding a relationship between the equilibrium constant and temperature in that way. I think that's more or less what I did for my IA. But it's convoluted and fun, but not terribly useful. It's fun for the IA though. It's great fun. So yeah, that's the thing. And I guess that's the first half.